Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's an honor today to have Ranjit Nair visit us from University of Southern California. He's a PhD candidate in the Team Core research group under Milan Tombe, and his interests include multi-agent systems, decision theory, and reasoning under uncertainty. He's examined in his PhD work the role allocation algorithms for multi-agent teams, in particular the application of teams that do search and rescue in urban disasters. And so take it away, Ranjit, talking about analysis of multi-agent teams using distributed POMDPs.
Hi, I'm Ranjit Nair. Thanks for that introduction, Eric. I'm going to talk to you about my thesis work, which is analysis of multi-agent teams using distributed POMDPs. So for the context of this talk, I'm going to define an agent as an automated software entity that can sense and affect its environment. And a multi-agent system is then a system which has multiple such entities that either collaborate with each other or they compete with each other. For example, you can have an auction on eBay, which is an example of a multi-agent system, or rush hour traffic on the 405. Multi-agent teamwork is a multi-agent system where now these agents are going to collaborate to achieve some shared goals. An example could be a convoy of cars, and you can see how a convoy of cars would be different from rush hour traffic on the 405. Or disaster rescue, where you have multiple rescue agents which need to save a city. Now, multi-agent teamwork has been applied to several realistic domains, and in particular, some of the domains here shown below are distributed sensors, disaster rescue simulations, battlefield simulations. And what you can grasp from these domains is that performance is critical, and it's often linked to things like loss of human life, loss of expensive machinery, etc. So knowing this about these domains, how do we analyze the performance of these teams? In particular, how will we evaluate the performance of the team? The domains have uncertainty in them. The actions that the agents take have many non-deterministic outcomes. Each agent doesn't know exactly what the world state is, so it's partially observable. And plus, the agents may or may not be able to communicate with each other. So each agent might have a different picture of what the world is. How would we then suggest improvements to the team plan that this team of agents is executing? In particular, how can we make improvements to the allocation and role allocation within these team plans? So traditionally, there have been two real approaches to multi-agent teamwork. One is the symbolic multi-agent teamwork approach. And this is based in teamwork theories like the joint intention theory and Conan-Levesque's theory on teamwork, and also several practical models that have been used to build real systems like the STEAM system or shared plans. And most of these approaches for multi-agent teamwork can be seen to be couched within the framework of beliefs, desires, and intentions. They've been applied to realistic domains. That's the advantage. But the con there is that they do not explicitly reason about the cost of actions or the uncertainty that exists in these domains. More recently, we've got the distributed POMDP model, or partially observable Markov decision problem. These are mathematically rigorous. It explicitly reasons about the cost of actions, about the uncertainty in terms of partial observability, the non-determinism in the actions. But finding the optimal policy is non-deterministically exponential, and hence it has been applied to only very small-scale problems. So what I'm going to present here is a hybrid approach, a hybrid between a symbolic BDI-based approach and the distributed POMDP approach. In order to do this, I'm going to define a role-based multi-agent decision problem. This is a kind of distributed POMDP. And I'm going to show how we can evaluate and analyze team plans in order to make improvements in them. So the idea is to treat the BDI team plan as a distributed POMDP policy, and then try and optimize key decisions within this BDI team plan, instead of optimizing optimizing the decision at every single decision epoch. So for example, if this is your domain, and you have, in a traditional BDI system, it consists of a BDI team plan, and this plan is interpreted by a BDI interpreter, and both these together give you what is called what I call as an incomplete policy. And this is incomplete in the sense that certain key decisions have been taken out of this team plan. Now this BDI team plan is applied in a particular domain, and we first can build a model of the domain, you call an RMTDP model of the domain, which exploits the structure within the team plan in order to come up with a factored RMTDP model. Secondly, now that we have an incomplete policy, we can search amongst the space of all possible completions. So we can search for completed policies, and again here we can speed up the search by exploiting the structure within the BDI team plan. And the third way in which the BDI approach and the POMDP approach can be used synergistically is a faster evaluation method for a RMTDP policy, which uses the belief structure which is used in the BDI team plans. As a result of this, we'll have a completed policy which can then be applied in the domain again. So the overall approach is to come up with is to use decentralized POMDPs for the analysis of real-world systems. We start with a team-oriented program, which is an example of a team plan. It consists of hierarchical team plan, an organization hierarchy, and a set of available agents. And I'm going to provide tools, RMTDP-based tools, which can make improvements to this team plan, come up with an improved team plan which can then be applied in a realistic scenario. So this is RoboCupRescue. I'm going to run a short demo now to show how the improved team plans perform. So this is a simulation of a city in Japan. This is Kobe, Japan. It's a 1 kilometer by 1 kilometer square block. There are two fires that are there once the simulation begins. One is at this corner of the map, and the other is at the other corner. There is an initially unknown number of civilians at each location where the fires are. We have two fire brigades at this location, another two here, and they're superimposed. And the fifth fire brigade at this fire station. And we have 5 ambulances which are co-located at this location here. And the problem is to try and determine which fire brigades to send to which of these two fires. And once the fire brigades get there, they will know how many civilians there are at each location. And then the question is, how many ambulances should we assign to each of these fire locations based on the information about where the civilians are. There's uncertainty in terms of how the fire will spread, and each agent can only observe the area immediately surrounding them, and also uncertainty about how the health of the agents will change. So here we're going to see the simulation. In the simulation, it's the allocation done by a human in our research group. I'm not going to name him because he actually did pretty embarrassingly badly here. So he came up with his allocation, and he was given as much time as he wanted to come up with the allocation. And as you can see here, this fire has been put out, shown with a blue color. And there is this ambulance is trying to rescue the civilians trapped here. At this corner of the map, you can see that the fire brigade, the fire engine which has been assigned there, has been unable to put out that fire, and the fire started spreading to the neighboring buildings. And so here we have a score of how well the team is performing. So you have information about how many agents are alive right now, what the health of each agent is, and so on and so forth.
What is the fire brigade not going anywhere.
It's trying to put out that fire. It's not able to.
This one here.
This fire brigade has already put out the fire. It's finished its task and it's gone and it's sitting in a refuge.
It cannot go to the other.
So the scenario has been set up such that it can only go to the fire that it's been allocated to.
Out of water.
Oh, God.
Okay, so as you can see, it does fairly badly, and all the 4 civilians who are located at this area at this fire die, and also some of the fire brigades end up dying. And so it's not a good scenario. In comparison, we can see the comparison of how the allocation does when it uses the RMTDP based method. So now this comes up with a different allocation of the fire brigades. So as you can see here, in the earlier case, only 1 fire engine was sent to this particular fire. In this case, 3 fire engines were sent there. This fire has already been put out. The fire engine has gone and sat in a refuge. And out there, that's where the fire has been, the level of the intensity of the fire has increased, but now it's been able to put it out. And it's now they're going to go and sit in this refuge here. So in general, this is able to save, I think, 1 of the civilians ends up dying. But it's definitely much, much better than the other case. I should point out here that this is just one particular run where the approach RMTDP-based method did exceptionally well as compared to the human. It's not the case that the humans always perform so badly, but in no case does the human outperform the RMTDP-based method. Okay, so other team plan frameworks are possible apart from team-oriented programs, for example, GP, or other multi-agent team planning frameworks which you might be familiar with. Also, all this analysis is done offline, and it assumes that the rest of the team plan is fixed. So only the key decisions that you're trying to optimize are kept open, and every other part of the team plan is fixed. Okay, so for this talk, I'm first going to give you some background on team-oriented programs. I'm going to tell you a little bit about distributed POMDPs and more about the RMTDP model. I'm going to show my algorithm for optimizing key decisions within the RMTDP model. And I'm going to show how this can be applied to a realistic domain, the RoboCupRescue domain. Okay, so here's an example scenario in order to explain some of this work. You have a bunch of helicopters which are initially located at point X, and the goal is to try and get them to point Y. There are 3 different routes that can be taken, Route 1, Route 2, and Route 3. These routes have different lengths and a different failure rate on each of these routes. The idea is that first, some of the helicopters are going to be assigned a scouting role. The scouts will go on ahead until one of the routes has been made safe, and then all the transports go along the safe route. Once a scout fails, it can be replaced by a transport, but a scout cannot become a transport later on. There's uncertainty in terms of failure rates on each of these routes. There's different observability on each of the different routes. And the probability of failure on a particular route depends on how many scouts you assign to that route. The goal here is to come up with the best allocation of helicopters to either the scouting role or the transport role. So how many helicopters should be transports? And amongst the scouts, how many of them should be on each of these different routes? Another question that I'll try and answer is, how should the agents reallocate themselves upon failure? Okay, so here's the team-oriented program for this particular domain. Here's what it would look like. So we have the organization hierarchy, which consists of a task force broken down into a scouting team and a transport team. The scouting team broken down into Scout Team A, Scout Team B, and Scout Team C. The plan hierarchy consists of an overall execute mission, which is broken down into do scouting, remaining scouts, and do transport. As you can see, there are relationships between the various subplans in the plan hierarchy. For example, shown with a solid arc here is an AND relationship, indicating that both these subplans need to be completed successfully for the parent subplan to be successful. Similarly, here you have an OR relationship indicating that at least one of these 3 subplans needs to be successful for scout routes to be successful. In terms of, you also have relationships, these are called temporal relationships, shown with a double arrow. it indicates that do scouting in this case needs to be completed successfully before remaining scouts can begin. Similarly, do scouting has to be completed successfully before do transport can begin. On the right hand side in these square brackets shows the sub-team in the organization hierarchy that has been assigned to the sub-plans in the plan hierarchy. So given an assignment of sub-teams from the organization hierarchy to various sub-plans in the plan hierarchy, what is the best allocation of agents to different leaf levels in the organization hierarchy? So in the helicopter domain, in the mission rehearsal domain, how many helicopters would you assign to Scout Team A, how many to Scout Team B, how many to Scout Team C, and how many to the transport team? The reallocation question is when and how should these agents reallocate? And for this I compared different reallocation strategies, and I won't be talking about that today, but if you want you can look at this work. It's work I presented at AMAS 2003. So here's a little background about MDPs, POMDPs, and distributed POMDPs. An MDP, or a Markov decision problem, it consists of a tuple SAPR, where S is a set of states, A is a set of actions that the agent can take, P is a function, a transition function, which tells you the probability of getting into state S dash, given that you performed action A in state S, and R is the real value reward that you'd get for performing an action A in a state S. The actions are non-deterministic, and this is the function. The function P is the function that tells you what the resulting state would be. The goal is to try and find a policy pi such that it's a mapping from a state to an action that maximizes the expected reward for performing that particular policy. And the complexity of finding the optimal policy is P-complete. So a POMDP is a generalization of an MDP, where now the single agent that we have in this problem, it doesn't know exactly what the world state is. So you have the same features as the MDP, except now you have omega, which is a set of observations, and O is the function which tells you the probability of receiving an observation omega, given that you're now in state S and the previous action performed was action A. So the state is partially observable. You only receive some observations omega about the state, and the goal is to try and find a mapping from the observation from each and every observation history to an action, and the complexity of this is P-space complete. And now to distributed POMDPs. Distributed POMDPs are a generalization of POMDPs, where instead of just having one agent, now you have multiple such agents, and A, omega, and R are now not they don't refer to individual actions, but joint actions, joint observation, and joint reward. The reward that is obtained is shared equally amongst the agents, and the goal is to find a mapping from the observation history of a particular agent to its action set. So we're trying to find local policies for each agent, and together they comprise the joint policy. And the complexity of finding the optimal such policy is non-deterministically exponential, and that's scary news. So the RMTDP model, or the role-based multi-agent team decision problem, is like all other RMTDP models. So it has the same features in its tuple. The key difference is that we separate out the actions of interest. So if we're interested here in role-taking actions, so we separate the actions into role-taking actions as well as role execution actions. And similarly, with the reward too, we divide the reward into reward for role-taking and reward for role execution. So here the policy that is used for action selection comprises of individual policies for each of the agents, and each local policy for a particular agent comprises of a role-taking policy and a role execution policy, where the policies are a mapping from the observation histories up to time t to either a role-taking action or a role execution action. So this theorem shows that if we decided to fix the role-taking policy, if we decided to fix the role execution policy, and we now try to find the optimal role execution policy, the role-taking policy, the problem is still non-deterministically exponentially complete. And that is depressing news. In fact, finding the globally optimal role-taking policy is going to be intractable. It's likely to be doubly exponential, and a brute force search requires requires so many different evaluations. So that's the number of role-taking actions raised to the number of observation histories likely raised to the number of agents. So that's clearly bad news. And so there are two approaches I take to handle this the intractability of this problem. One is to separate this role-taking policy into role allocation and role reallocation analysis. And the second is to improve the complexity of each of these evaluations. So in order to evaluate a team-oriented program, you have a value function, which consists of your initial reward, your immediate reward for a particular observation history, and the future reward you get. The key thing to note in all this math is that the policies are now going to be indexed by the observation histories of each of the agents. And the idea is to, instead of maintaining these long observation histories, we maintain a set of privately held beliefs, and beliefs are beliefs in the belief, desire, intentions sense. They're nothing but propositions that the agent believes to be true about the world. Sure.
So is it true that each role has its own policy, or each agent has its own policy?
It would be the case that each agent has its own policy, but it might be in a particular domain, it might be the case that you can have policies for individual roles. So in the general case, it would be the case that each agent has a particular policy.
So one of the things you're doing is trying to factor the policies across roles and agents in a way that makes things more tractable. Is that a fair characterization?
That is it.
And is it also true that the third type, the distributive POMDP, can you emulate that with a standard old POMDP?
Not if you wanted to find the globally optimal policy. If you wanted to find locally optimal policies, you could treat it like a single agent POMDP. I can talk at more length about that later on.
Okay.
But it's the answer is no. You cannot emulate a single agent POMDP by a distributed POMDP.
So you mean
That you cannot emulate it unless you give up on optimality.
Okay.
So this is how an agent, which is in a BDI agent, would update its beliefs. Would be by every time a new observation arrives, the agent applies its belief update function in order to update its set of privately held beliefs, and these privately held beliefs are used in the BDI team plan in order to do action selection. So the idea is, if the agents are in the BDI team plan are going to use their privately held beliefs and not the observation histories, why not index the value function by the privately held beliefs? And this gives you a different expression for the value function, where instead of the observation histories for each agent, we're now using the set of beliefs that each agent holds. And so it's exactly the same formulation. You have an immediate reward and the expected future reward, but the update in the belief state is now done using a belief update function instead of in the earlier case where you simply append the new joint observations to the existing observations.
Why isn't there a discount factor?
That's up to you to add it. It doesn't change the complexity. Okay. So here are the complexity savings. Here, in this case, as you can note, in the case of where you maintain the observation histories, there is the time horizon over which you're doing the evaluation is in the exponent, whereas when you use the privately held belief sets, then you have the time horizon moving into the as a factor, and this gives a significant improvement in the runtime for the evaluation algorithm for a team-oriented program, and I'll show you the empirical comparison in a couple of slides. So here's how we would optimize the key decisions within the team-oriented program. So let's say that the key decision we're interested in right now is role allocation. This represents your the organization hierarchy, and the organization hierarchy can be translated into a role allocation space. So for example, if the task force consisted of 6 helicopters, these 6 helicopters could be broken down into 0 in the scouting team, and 6 in the transport team, or 1 in the scouting team, 5 in the transport team, and so on and so forth. Essentially all the combinations. Similarly, that 1 scout which is in the scouting team could be put in either scout team A, scout team B, or scout team C. Essentially now, if you look at this, every single leaf node in this allocation space is a complete allocation. And the problem is to try and determine which amongst these leaf nodes is going to be the best allocation for your particular team-oriented program. The numbers in the right-hand side are what I call max estimates, and they're nothing but upper bounds on the value of a particular leaf node. So for example, 4167 is an upper bound saying that no child can have an evaluation of greater than 4167. And the key is to try and find these upper bounds as quickly as possible in order to do a branch and bound search in this role allocation space in order to come up with the best allocation. Each of these leaf node evaluations here is a complete RMTDP policy evaluation, and we want to try and reduce the number of such evaluations necessary. So let's say we could come up with the max estimates, and in the next couple of slides I'll explain how we come up with them. We then arrange the parent nodes in order of their max estimates, evaluate the children below them, and use the evaluation of the children to prune out other parents in the role allocation space. So this proceeds until you find the role allocation at the leaf level with the highest value. So this is a branch and bound search which uses these max estimates of the parent nodes in order to prune the space, reducing the number of leaf level allocations that are necessary. And this is it's a complete algorithm, it's an exact algorithm. I'm going to now explain to you how the max estimates can be computed. This relies on being able to decompose the RMTDP into smaller RMTDPs. So the idea is to try and identify components in the plan hierarchy in order to decompose the RMTDP into smaller RMTDPs. So the first thing you can identify are components which have temporal constraints between them. So for example, between do scouting and remaining scouts. And also components which are completely independent of each other. And once you have this, you can obtain smaller RMTDPs for each component and exploit this decomposition in order to do a fast component-wise computation of these max estimates. So now we are going to go through an example of a particular parent, evaluation of how we can compute the max estimate for a particular parent in the allocation space. This is a third parent in the allocation space which basically had 2 helicopters in the scouting team and 4 helicopters in the transport team. So the first step is to try and identify the start states and the starting observation histories of each of these components independently. Now for the very first component in this out here, the start states are nothing but all the possible initial allocations to the agents to the different sub-teams. But for subsequent components, like the do transport component, the start states are nothing but the end states from the previous component. So if you could identify the end states from do scouting, those would be the start states for do transport. Similarly, the start states for remaining scouts are the end states of do scouting. And similarly for the observation histories, the starting observation histories for the very first component would be null, no observation so far. But for subsequent components, the starting observation histories are nothing but the ending observation histories of the previous component. And once you have the starting components, the start states of each of these components, and you have the starting observation of each of these components, you can find the expected utility of each of these components independent of the other. So the key thing to note is that by identifying the end states of one component as being the start states of the next, we've been able to decouple these components, this evaluation, into a component-wise evaluation. So in this particular case, we can find the max estimate by summing the expected utility of each of these components. So for the max, so I call this the max TXP value for a parent node, and that's computed using these values in the right-hand side in square brackets. Those are the values for each of these components computed independently. So the question you might be asking is, where do these savings come from? And the main reason why you get saving is because we're avoiding duplication of evaluation. So at the end of a particular component, you're going to collect all the end states of a particular component before starting evaluation of the next component. So if you had multiple start states of the first component, which resulted in common end states for that component, then these can be combined together to get a smaller set of start states for the next component. Similarly, not all variables in a particular end state are necessary for the subsequent component. So for example, in the scouting, in this example of the helicopter example, the do scouting component had various various end states which had values about where exactly the scouts failed, etc. But the do transport component only needs to know which of the routes was safe, and all the transports would go along that route. So it's no longer important to maintain all the variables which were important for the first component. And so you're now dealing with a smaller set of relevant variables, and you can remove the irrelevant variables from the end states, and this results in a smaller set of start states for the remaining components. Similarly with observation histories. Not all the observations in the observation histories will be actually relevant to the subsequent components. Maybe the sequence of the observations is not important. Maybe certain observations aren't too important for the subsequent component. So these irrelevant observations can be removed, resulting in a smaller set of observation histories. So here's a comparison of the of different approaches in order to compute the max estimate, in order to find the best role allocation. The no-fail heuristic assumes that agents do not fail. And this is an assumption made only for the computation of the max estimate. So we're still going to it's still an exact solution. It's going to find the same best role allocation, except that it uses a different it uses a heuristic in order to find the max estimate. In this particular domain, assuming that agents don't fail results in much less branching in the evaluation, and it's valid in all those domains where once a failure takes place, you're not likely to get more reward than if there was no failure at all. And we can use several other heuristics that guarantee completeness, guarantee correctness. For example, you can assume that that it's a completely observable world, and that's only for the computation of the max estimate. And once that is done, you can use these max estimates in order to find the best role allocation. Here's a comparison in terms of the number of nodes evaluated in the role allocation space of no fail, max EXP, and no prune. No prune is nothing but a brute force search of all the leaf nodes in the role allocation space. So we find that there's a 20-fold reduction in the number of nodes for no fail and max EXP over no prune. And max EXP actually evaluates fewer nodes than no fail. So in the case of 9 and 10 agents, you find that max EXP actually evaluates fewer nodes, but the max EXP computation itself is more complicated and it takes more time. Here's a comparison in terms of the actual runtime. No prune Bell basically uses the belief-based observation method, and no prune obs uses the observation history-based method for evaluation of a node. We obtained 12-fold speedup for no prune Bell over no prune obs for 7 agents. 14-fold speedup for max EXP over no prune Bell for 7 agents again, and a 47-fold speedup of no fail over max EXP. So now let's talk about the RoboCupRescue scenario, the more complicated scenario. I explained the scenario to you already. There are 2 fires at 2 ends of the world. There are a total of 5 civilians. Initially, the number of civilians at each fire location is not known ahead of time. There are 5 fire engines in all, 2 at this location, 2 at this fire station, and 1 at the 3rd fire station, and 5 ambulances all at 1 ambulance center. The goal is to try and allocate fire engines to the different fire locations, and once you know how many civilians there are at each location, the goal is to determine how many ambulances to send to each of these locations. Initially, the number of civilians at each fire is not known. There's partial observability, which arises from the fact that agents can only view a certain radius around them, and there's non-determinism in the environment in terms of how the fire spread and how the civilians' health deteriorates. So here's a comparison with 3 human subjects from our research group. They're all people familiar with the RoboCupRescue domain. They were given as much time as they wanted to come up with their allocations, and they were told that the civilian distribution, they were asked to come up with their allocations for 2 cases of civilian distribution. Initially, they were told that the location of the civilians were going to be drawn from a uniform distribution. or in the for the second case, they were told that the distribution of the humans was drawn from a skewed distribution where at phi 1 initially, where there will be with a probability of 0.8, there'll be 4 civilians, and with a probability of 0.2, there'll be just 1 civilian. And here's a comparison in terms of the number of civilian casualties for the RMTDP versus the human subjects. And the fifth set of bars here is the agents fielded in 2001 at the RoboCupRescue competition by us. So in terms of civilian casualties, human 2 seems to have done really badly, but RMTDP does better than both the human subjects as well as the agents you fielded in the competition in terms of the number of civilian casualties. The amount of building damage was almost the same for all 5 allocations used. There were 5 civilians in all. So here the RMTDP has been about to save about little less than 2 civilians. Sorry, there were little less than 2 casualties.
So this was, you ran your algorithm like several times?
The algorithm was run once. It came up with the allocation, and then in the actual RoboCupRescue simulation, 40 simulations were run for each data point in order to come up with the actual performance values. Here's a comparison in terms of when the allocation used was when the distribution of the civilians was according to the skewed distribution, and in this case the RMTDP's performance was the difference is even more stark. In both these experiments, the t-test was done in order to compare the inequalities in these allocations, and it was found that the RMTDP was significantly superior to both the human as well as rescue ISI in most of the distributions of the different civilians, and in no case did they and they were the same in all other cases. So in no case did RMTDP do actually worse than the humans or rescue ISI. So in summary, I should talk to you about the marriage of a BDI and POMDP approach, and this allowed for solving larger problems than could have been solved if you used only the POMDP approach. I talked about the RMTDP model for analysis of role allocation and role reallocation, and showed how we could optimize key decisions within the policy instead of optimizing every single decision epoch. This used a novel decomposition technique based on the structure in the plan hierarchy. I also talked about a belief-based evaluation of policies, and in my papers you can find how to compare different role reallocation strategies and also form a family of local perturbations of these reallocation strategies. And I talked about an application to a complex domain. Since I have some more time, I'm going to talk to you about another aspect of my work, and this is in a search for locally optimal policies for distributed POMDPs. So this is a bit of a context switch to give you a little more idea about this problem. In the first case, we started with team plans, and we tried to make improvements to these team plans. We tried to see how we could improve role allocation in these team plans. In this part of the talk, we're going to assume that there are no team plans to start with, and we're trying to synthesize a policy for the team. Okay, so we're trying to solve that problem which I said was NEXP complete. Okay, so we're trying to find the optimal joint policy for a distributed POMDP. It's non-deterministically exponentially complete in the general case, and the reason for this high complexity is that you need the reward that the agents get depends on the joint reward it depends on the joint reward of the team, and that joint reward depends on the actions that the other agents perform. And so you need to reason not only about the world state, but also what actions the other agents are likely to perform, which depends on the observations that they observe. The approach that I'm going to take is, we call it the joint equilibrium-based search for policies. The idea is fairly simple. It exploits the fact that there are multiple such agents and they're cooperative, so we can have a centralized planner in order to come up with the policies for the different agents. And the idea is to find the best policy for a single agent by fixing the others, and to iterate through the agents until you converge. And then I also have a dynamic programming-based approach to reduce the complexity of finding the best policy for a single agent fixing the policies of all the other agents. And I'm going to show how this results in potentially exponential savings in time complexity. And I'm going to compare the joint equilibrium-based method with the global search algorithm in terms of finding the best, in terms of finding the optimal policy. Okay, so here's a little bit of literature survey. So in the space of multi-agent POMDPs, there's a lot of people who work in making assumptions that the world is individually observable. So that's where they assume that each agent knows exactly what the world state is. Then there are a bunch of folks who assume that the world, if all the agents pool in their observations together, then they would know exactly what the world state is. And my work resides here, where even if the agents were to put in all their observations together, they need not know what the world state is. Okay, so I'm going to talk to you about an illustrative example. I'm going to explain how to find the, explain something about the complexity of the globally optimal algorithm. I'm going to talk about the joint equilibrium-based search for a policy and a dynamic programming approach for which would do this search for the optimal policy. And I'm going to talk about the complexity savings and some empirical results. So here's a scenario. It's a kind of toy scenario which is very interesting. We have two agents who are in a corridor facing doors A and D. Now behind the doors are either a tiger or a large amount of money, a huge amount of money. Now the agents don't know exactly which door the tiger is behind. It could be either behind door A or door B. And that's drawn from a probability distribution known ahead of time. And the agents can perform three actions. The agents could choose either to open the left door, open the right door, or they can choose to listen closely behind the door. Now, the reward that the agents get is a shared reward, and the reward depends on whether the two agents open the door together or not. So if they both open the door behind which the money is, they get double the reward they would get if only one person opened it. If either of them open the door to the tiger, they're going to get mauled. But how badly they get mauled depends on whether one of them opens it or two of them open it. If they both open the door to the tiger, they're going to be mauled less than if only one of them opens the door to the tiger. The listen operation gives the agent some more information about where the tiger is. So this action has, it's still got some noise associated with it, but it makes the agent more confident about where the tiger is. So it has a small cost, but it's still a little unreliable. The agents in this scenario cannot communicate with each other, and the problem is reset every time one of the agents chooses to open one of the doors. Now, this is because of the nature of the reward function. Agent 1 has to reason about what did agent 2 hear. Because if the agent 2 heard a particular thing, agent 2 might decide to open the door. So what should agent 1's response be? Similarly, agent 2 is going to think about what did agent 1 hear. So it's necessary to reason about the observations of the other agents and not just about what the world state is. So the question I'm going to try and answer is, what is the best joint policy over some finite horizon T?
Wait, in that problem, there's no communication, but each agent can observe what action the other agent took, or no?
You cannot, you know what reward you get, and so you can reason about what action you got, what the action the other agent took.
But not about what they heard.
You cannot, so you can reason explicitly based on what you've heard, but what they're likely to have heard.
But they don't communicate.
But they don't communicate. I've done some more recent work where they are allowed to communicate, and I might be able to talk about that briefly.
Is that a standard problem, or did you?
So the single agent tiger problem is the standard problem, which is, I think Leslie Kaelbring talked about this problem in one of the single agent POMDP works. And it's a classical AI problem which they talk about, the tiger problem.
Can you listen more than once?
The problem is you can listen as much as you want.
There's no cost.
There's a small cost associated. Okay. So we have a single offline centralized planner, and the algorithm works such that you fix a particular agent, you fix the policies of all the other agents, and you find the policy for the particular agent I that maximizes the joint reward of all the agents together. So it's like a best response algorithm. It's guaranteed to converge to a Nash equilibrium, and we can do random restarts in order to find the global optimal. And an exhaustive version of this requires these many, this is going to be the complexity of finding the policy which maximizes the joint reward for a particular agent I with respect to a fixed policy for all the other agents. And this value here, this first part is nothing but the number of policies for a particular agent I, and the second part here is the cost of evaluating a joint policy. Okay, so the idea is now to try and reduce that complexity using dynamic programming. And so this is going to rely on the fact that you can incrementally construct the best policy. So basically the optimal policy for the last t minus t steps is optimal given the observations over the first t steps. So in a single agent case, a single agent POMDP, it's enough to reason about the world state. So you can reason about the world state S given the agent's observations. And this is shown to be a sufficient statistic in order to find the optimal policy. But that's not the case in a multi-agent case. So in a multi-agent case, the belief state defined as a distribution over the world state is not sufficient. And in particular, we need to reason about the world state as well as the observations of all the other agents. So we define a new extended state, which consists of the world state and the observation histories of all the other agents. And using this, we can now, using the extended state as the world state, we see that this problem becomes a single agent POMDP. So if I now explicitly have the observations of all the other agents as part of my state, the problem is a single agent POMDP with a slight difference that we need a new transition function which can be obtained from the transition function of the individual agents and the observation function of the other agents. So here's where you're actually explicitly reasoning about the other agent's observations. And you define a new observation function, which depends on the observation function of a particular agent. And once you've done that, you can also define a new multi-agent belief state, which is the distribution over this extended state, given your observation history and your previous actions, and the initial distribution over the start state. So here's what the algorithm looks like for the dynamic programming approach. You find the reachable states the reachable belief states at every time step t. And for each of these belief states, you compute the value function associated with each action and that belief state. It's a simple value iteration algorithm. So you have the value function, which consists of your initial reward and the future reward. And your immediate reward consists of the reward you obtain for each of the extended states, multiplied by the probability of that observation, of that extended state. And then we can just translate your value function using argmax of the actions into the policy for each of the individual, for the agent I, for the agent 1 whose policy is not fixed. So here are some complexity results. I'll go over this now. So here's the difference in the complexity of the exhaustive approach to finding the optimal policy, and here's the dynamic programming based approach. As you can see, we've been able to get rid of this. This results in an exponential savings in terms of time. And there's a lot of savings in terms of space as well. We can see empirically what the savings are in this slide. So here's a comparison of doing a global search for the optimal policy versus doing a search for the locally optimal policy. In general, you can find for a particular reward structure A, we were able to find the globally it always was the case that the locally optimal policy was the same as the globally optimal policy. We changed the reward function, and as you can see here, we actually get this. If you use a reward structure B, a reward function B, we got a different reward for a different reward using the locally optimal policy. Here's a comparison of the number of policies evaluated. And so here in light blue is the globally optimal policy search. And in general, there's a huge amount of savings in terms of the number of policy evaluations that are necessary using each of these methods. Here's a comparison of how much you can scale up using the exhaustive method for finding the policy versus the dynamic programming method. the dynamic programming method couldn't be run in a reasonable amount of time for more than 3 agents. I'm sorry, the exhaustive approach could not be used for more than 3 agents, for a time horizon of more than 3, whereas the dynamic programming approach scaled up to a time horizon of 7 in about 30 seconds. So here's a summary of the talk then. Finding the globally optimal joint policy is intractable. Hence, we used the search for a locally optimal policy. It exploits the fact that we have multiple cooperative agents, allowing you to have a centralized planner. You find the best policy for a particular agent by fixing all the other agents, and you repeat this until convergence. I came up with the dynamic programming approach, which used a new sufficient statistic, which is a distribution over an extended state instead of a single agent state. This results in converting the problem into a single agent POMDP. And I showed how we can obtain exponential savings in terms of time complexity. And empirically, I showed a comparison of JESP versus the globally optimal search, as well as JESP versus the exhaustive approach to JESP versus the dynamic programming approach to JESP. Sure.
Is it the case that what allows you to break down this problem into a single agent POMDP is just the nature of the task, nature of the problem in which there's no communication? So that allows you to be able to assume that each agent's beliefs are independent of each other?
Actually, that's not the case.
Okay.
In more recent work, this is work which I've just recently published, we actually introduced communication explicitly. And the communication that we introduced is communication where if I communicate with you, I will share all my observations, or my entire observation history since the last communication. And you're forced to communicate with all your observations since your last observation with me. And we now arrive in a synchronized state. And this results in both higher reward, because they're now much more coordinated, as well as the fact, and also it results in savings in terms of time complexity as well as space complexity. And we can scale up much more than what I showed in the previous slide. And the reason you get these savings is because every time the agents communicate with each other, they now no longer need to, they're in a synchronized state, and they can throw away all their observation histories. And by having fixed policies for communication, we can have even further savings, which allow you to would put explicit bounds on the size of the policy and the complexity and the amount of time the algorithm takes to run. Thank you very much.
Additional questions or comments? I had another question about the first part where you found that the RMPP approach did statistically better than the other than the humans, and I guess some other approach.
Right.
Now, is it the case that that was true for the people, the lives that were saved, but not necessarily for the building?
For the building damage, they all did almost the same. Yes. So it was about civilian casualties.
Now, is that just a reflection of the reward that you just get more reward saving people than you do saving buildings?
That's actually right. And when the people were told about this particular experiment, they were told they were going to be graded primarily on the number of civilian casualties, and the secondary evaluation criteria would be the amount of damage to buildings. And that actually is is what people use for evaluation in the actual RoboCupRescue competitions as well, where human life is considered higher than damage to buildings.
So on related work in this area, so what would you say is the most related work going on to your work?
In terms of the locally optimal approach, the most related work is work done by Claudia Goldman at UMass with Victor Lesser, and there the key difference is that they consider the world to be completely observable for each. So each agent has a local state, and each agent knows its local state completely. but it doesn't know what state the other agent is. And that reduces the complexity of the problem drastically, and they have a different approach to solving it. But the idea is similar, where you fix the policy of one agent and try to find the policies of the other agent. I haven't seen much related work in terms of marrying the concepts of BDI and POMDPs. The closest I can see is work done by Mike Woolridge and his student Martin Shute, and I think Simon Parsons collaborated with that work. And that was in marrying, it was a single agent case, and they used POMDPs in order to do intention updation for a BDI agent. So yeah, that would be the closest related work. Thank you.